So a lot of the things that we notice with derivatives hold true for integrals as well. So here's one idea. This is saying if you are taking the integral of two functions that are added together, you can just take the integral of each one separate. This is very similar to an idea that we learned with derivatives. If I gave you x cubed plus 5x and you had to do the derivative, what did you do? You did the derivative of the first one separate and the derivative of the second one separate and just added them together. So you basically took the derivative of each one separate and just added them. The same thing happens if you're working backwards. If you're working backwards, you can do the integral of this one and the integral of that one separate, and then just add c in the end. So for this first example, integral of x to the 5, add 1 to the exponent and divide. Add 1 to the exponent and divide. Integral of 2 would just be 2x plus c. Now, just like we learned, yeah, I can go back for a second. Now, I was going to say, just like we learned for derivatives, sometimes we get something in a form that we don't know how to find the derivative of. And so we might need to do some algebraic manipulations first in order to make it easier. So in this case, I've got x plus 7 times by x minus 3. We haven't learned any integral techniques for when things are multiplied together. We know that when you took the derivative of two things multiplied together, well, you had the product rule, or you could simplify it first and find the derivative using other rules. So if, for example, this was a derivative question, you could use the product rule. And you could say derivative of the first, keep the second the same, plus derivative of the second, keep the first the same, and you'd get the right answer. But if you multiplied this out first, then the derivative is really simple because you can just do the derivative of each one separate. And it's actually probably easier in this case to multiply it out and do the derivative of each one separate than it would be to use the product rule and simplify after anyways. Well, the same thing happens with integration. So if we multiply this out, now I know how to do the integral of each one of these separately. Because each of them are power rules, so you can just add 1 to the exponent and divide by that number. Same thing for this case. Any ideas on how to make this simpler? Factor the top. Let's see if that happens. So if we factor the top and have x and x, minus 2 and minus 4. Does that work? Yes, it does. And then the minus 2's cancel. And now the integral of x is just going to be x squared over 2. The integral of 4 is minus 4x plus c. Oh, yes. Thank you. There you go. Another general result is that if you have a constant multiplied by a function, you can pull that constant out in front and it doesn't matter. So as far as a simple example goes, if we were doing the integral of 12x dx, we could write that as 12 and then just do the x by itself. Add 1 to the exponent and divide by 2. That's the basic idea, that 12 can just stay out in front, which we've done in the examples up till now anyways. But sometimes you're going to get into some situations where you have to manipulate general equations like this. And so it's important to know if you have a constant there, it doesn't matter if that's inside or outside of your integral. So for this one, we're going to start with what you would probably want to do. And then we're going to run into a problem. Okay? So this is probably, I'm just guessing this is maybe what you want to do. You change that to a power, so you get x to the minus 1 dx. And then you want to add 1 to the exponent, right? And something feels like something's going wrong here, right? And then if you look back at our notes, we said it doesn't work when it's equal to minus 1. So this part is probably what you would want to try, but it doesn't work out. So what I'm going to do is I'm going to rewrite this. I'm going to pull the 20 out in front to write this as 1 over x. And I'm going to ask you, have you seen that derivative somewhere before? Because you're working backwards. And this is what makes working backwards harder than working forwards. Because if I ask you to find the derivative of, what's the derivative of natural log? It triggers something. Well, maybe it doesn't trigger something. It's 1 over x. If you got y is natural log, then y prime is 1 over x. Okay? So up till now, we've been learning derivatives. And what you've been doing as you've been learning them is you've been telling yourself certain triggers. And your brain, hopefully will get there, where you see natural log, and you go, derivative's 1 over x. And you only think of 1 over x if you get that hint of natural log first. Because that's how you train your brain to do certain things. If I see something, I can do the next step. What's going to happen now is they give you the next step without seeing the original thing, and all of a sudden it's harder to see it. Because you've trained yourself, if I see natural log, I do 1 over x. Now you've got to retrain yourself to say, natural log of x and 1 over x go together. I have to be able to see one and see the other at any time. So when I see this, I'm going to say this is equal to 20 natural log of x plus c. So all of those integrals that we did, we now have to see them backwards. Right? You see secant squared. Working backwards, you'd think, 10. Right? What about those other ones with cotangent and cosecant cotangent and all that? Those are probably a little rusty. Here's another general idea. If you have a derivative inside and you take the integral, can you see that they cancel each other out? Right? If I asked you to find the derivative of x squared, you'd say that's 2x. And then if I said, well, what's the integral of 2x, you get back to x squared. Because they just sort of undo each other. It's sort of like, okay, I'm going to get you guys to do some mental math. Pick a number between 1 and 10, someone. 3, okay? Now I'd like you to multiply that by pi squared and remember 8 decimal places. Good. Now I would like you to divide by pi squared and remember 8 decimal places. What do you get? 3. Good job. That's amazing mental math. I couldn't do that pi squared. I got lost, but I'm glad you're smarter than I am. So you realize that if you do something and then you undo it, you're right back to where you started from. That's all this general result is. If I take the derivative and then I untake the derivative, I just get the function that I started with. So how does this look like in a question? Well, inside this d dx is take the derivative of 5x squared. So if we would show all of our work, we would say, well, the derivative of 5x squared is 10x. So now I have 10x dx. Now, integral says, well, let's do our integral. That means add 1 to the exponent and divide by the exponent and then plus c. So what do I get? I get 5x squared plus c. So you could show all of your work, or you could notice that, yes, these two things are just going to cancel each other out. But because we did the integral last, we still have to do plus c. If we would have done the integral first, there's going to be no plus c. Again, we're doing integral first and then taking the derivative. Those two things are going to cancel each other out. If I showed all my work, this is what would happen. So here's this example. It says do the integral first, so inside I'm going to add 1 to the exponent, that'll be a negative 2, divide by that, negative 2, and then I'd have to do plus c. Then if I took the derivative, well, the derivative of this means the negative 2 would come out in front, subtract 1 from the exponent, and then the derivative of c is 0. And if you simplify this, you get 5x to the negative 3, which was exactly what we had inside to begin with. But notice this time there's no plus c, because you did the derivative last, and the derivative of the plus c would just be 0. So subtle differences depending on which one you do first and which one you do last. But basically, what we're seeing here is that they cancel each other out. Okay, so there's some homework here for you, or at the bottom of that page, to start practicing